Hello everyone, welcome to the next part of complex numbers. Today we'll be covering the conjugate root theorem. So this theorem simply states that for any polynomial with real coefficients and degree more than or equals to 2, complex roots occur in conjugate pairs. So let's dissect this a bit. Real coefficients. So a polynomial like this will have real coefficients because all the coefficients are real. Something such as this does not have real coefficients. So this means that the conjugate root theorem does not apply for those with imaginary coefficients. However, if you look here, for most questions, they will not give you imaginary coefficients because they want you to apply conjugate root theorem. So this condition over here with real coefficients and degree more than or equals to 2, just be sure to take note. Let's dissect the last part. For any polynomial, basically with these conditions, complex roots occur in conjugate pairs. So do you remember what a conjugate is? For example, if I have 2 plus 3i, the conjugate will just be 2 minus 3i. Complex roots will occur in conjugate pairs. That means if 2 plus 3i is a root, this also means that 2 minus 3i is also a root. That's what it means by conjugate pairs. So let's start by doing this question. Find p given that 1 minus I is a factor of 2z cubed minus 3z squared plus 2z plus p. So if 1 minus I is a factor, this means that 1 minus I is a root of this polynomial. So the other root, as per the conjugate root theorem, will just be 1 plus I. So we know that 1 plus I is a root by the conjugate root theorem. But we're missing out one more root. And what I want to do is actually split this into factors. Remember, when you have a quadratic equation, for example, x squared plus 5x minus 6, what you can express this is in terms of two factors, x plus 6 and x minus 1. You have two factors. And again, for a cubic, you can also express this in terms of all the roots, x minus alpha, x minus beta, and x minus gamma, where alpha, beta, and gamma are your three roots. So let's use this property. This will be equals to z minus your first root, which is 1 minus I, z minus your second root, which is 1 plus I, and z minus your third root, which we'll call a. We actually know that a is going to be a real number. Why is this so? Because complex roots occur in conjugate pairs. You have 1 minus I and 1 plus I as a conjugate pair. A doesn't have anything to have a conjugate pair with. And if you see in front, I'm missing out a certain number. Actually, I need to times this by 2. Because if you look at the coefficient of z cubed, on the left hand side is 2z cubed, and on the right hand side, we need this also to be 2z cubed after we do our expansion. So to find p, let's do our simplification on the right hand side. Alright, this looks like a little bit of a monster in terms of simplification. So what I'm going to do is a little trick. If you're not familiar with the sum and product of roots, you can just skip this part and do rainbow expansion. Okay, but rainbow expansion will probably take like 1 or 2 minutes longer, especially with all the simplification afterwards. You have this as z squared minus the sum of roots times z plus the product of roots. This comes from the fact that the sum of roots equals to negative b over a, and the product of roots is equals to c over a. Okay, so let me use this fact to help us. We write the 2 outside, and then we take z squared minus the sum of roots, which is 1 minus I, plus 1 plus I. In this case, we'll just get this as 2. And then we have a z outside over here, plus the product of roots. The product of roots is 1 minus I times 1 plus I, which we'll get as 2. Because by the difference of 2 squares, we'll get this to be 1 minus I squared when we multiply them together. And that just nets us 2. As you can see, this method helps us simplify things really quickly. Okay, we can simplify this in a matter of just 10 seconds. And we have the z minus a at the end. Alright, now we have no choice but to do our simple rainbow expansion. So we take 2z cubed minus az squared minus 2z squared plus 2az plus 2z minus 2a. And then we have our final simplification where we multiply the 2 in. So remember, we want to find p. P in this case, the constant term, we'll get that p equals to negative 4a. So that means we also need to find what a is. And what can we do? We can again compare the coefficients of z. If we compare the coefficients, we get 2 equals to 4a plus 4. So again, we get 2 equals to 4a plus 4. And after we do our simplification, we get 4a equals to negative 2, which means that a equals to negative half. And remember, again, if we compare the constant term, we get p equals to negative 4a. So what p is just negative 4 times a, which is negative half. And we get p equals to 2. Okay, this is a very important IB question over here that will net you about 5, 6, or sometimes even 7 marks, okay? So please be sure to remember how to do these kinds of questions. Before the video ends, I want to show you a trick that you can do to find the roots, whether real or complex, of any polynomial. Let's go into our calculator over here. And let's say with our polynomial from earlier, 2z cubed minus 3z squared plus 2z plus 2. Now what I'm going to do is go into the menu, and then I'll go to Algebra, Polynomial Tools, Complex Roots of a Polynomial. Or you can just simply type in C poly roots. Then we'll do 2z cubed minus 3z squared plus 2z plus 2. And then we'll put a comma z. Why we have to write this comma z over here is to tell the GDC that we're trying to find the roots of the polynomial in terms of z. So we can press enter, and those are all our roots. This is just a little trick that I want to show you. Thank you so much for watching, and I hope you have a great rest of your day.